Hi there, thanks for joining us on this episode of Space Nuts. My name is Andrew Dunkley, your host, and coming up we're going to be looking at a dark energy survey that's got people questioning, well, of all things, the cosmological constant. We'll also be looking at a megastructure that's been discovered, and when we say megastructure, this is not a human-made thing. This has been made by the universe itself. The trouble is it is so big, they're now wondering how it's possible that it exists. I mean, it exists, it does, but people are scratching their heads. And we'll do a bit of a Peregrine update, which is not a very good update at all. And plenty of questions. We've got a whole bunch to get through this morning. Today, tonight, this evening, this afternoon, whatever time it might be where you are. All coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to unravel all those mysteries and much, much more is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How's it going?
I am well. Do you like my shirt? This was sent to us by Marie-Claire Mercier, who went to the DART mission at NASA, and she promised to send us some bits and bobs, and I'd just like to say thanks for my amazing T-shirt. Judy says my colour is blue, so there it is. And the DART sticker and the Planetary Defence Coordination Office sticker, and she even threw in one of these, Artemis sticker. And I'm guessing I'm now a member of the Planetary Defence group because I got a Planetary Defence badge as well. So thanks, Marie-Claire. That's so generous of you. Really appreciate it. That's great gear. What's happening in your world, Fred?
Well, it's been a nice busy weekend. We were in New Zealand doing talks at the Central Star Party in the North Island. You just reminded me, though, with that planetary defence button that you held up, for those who could see it. This time last year, when I was at the UN in Vienna, principally there to be part of Australia's delegation talking about dark and quiet skies, the issue of, the pollution by satellite constellations in particular. I also attended a meeting of the planetary defence body, the branch of COPUOS, the Committee on the Peaceful Uses of Outer Space, that looks after planetary defence. So I had a couple of hours with them, which was really fascinating stuff. And in fact, what they were doing at that time was, because there was a big planetary defence meeting coming up, this would have been last year in Vienna, and they were essentially setting up a scenario which was going to play out in real time during the meeting that they were planning, which was about what you do if there is an asteroid with a high chance of impacting the Earth and one that is, significant enough to warrant global action. And this scenario was being set up with incredible detail. For example, so I think it was a 1 kilometre or thereabouts, maybe 500 metre asteroid that they were postulating. Now, our detection systems are currently such that finding something like that should be easy. But so they had to work out a way where it would sneak through our planetary defences. Indeed, they did. They had an orbit for it that would have brought it in more or less from the direction of the sun. And so this was all laid out in great detail. I don't know how it went in the end because I wasn't part of that meeting, but imagine the urgency which would accompany something like that running along through a scientific meeting. It's quite amazing stuff.
Yeah, that'd be a really great exercise to witness, I reckon. Be fascinating to look at how they worked out what to do about it, if anything. But that's what this is about, though, the double asteroid redirection test.
Yes, it is.
Which was done year before last now, wasn't it? They're trying to find ways of deflecting these things should we ever have one that threatens the planet. Fred, let's get on to topic one, which we'll rush over pretty quickly because it's a fait accompli now. The Peregrine lander that was being sent to the moon, which was unfortunately leaking propulsion fluid or fuel, whatever you want to call it. Mission appears doomed. Well, now they've been keeping an eye on it. They've been keeping us informed. They were hoping there might be a way of resurrecting some of the mission targets, but it appears, should I say, all is lost?
Yes, that's right. So now the information I have on this is a few days old. It's about 3 days old, Andrew. Mm-hmm. But the company that operates the Peregrine lander, Astrobotic, were releasing news that they expect that it would actually, on its orbit, would bring it back so that it would re-enter the Earth's atmosphere and most likely would burn up in the Earth's atmosphere. And so what they've been doing is, using what time they've got to do as many scientific experiments as are possible, because I think there was at least one of the NASA payloads that was on the Peregrine spacecraft that actually, I can't remember which one it was, but could be used to make useful measurements in transit rather than waiting for a landing on the moon. So the landing on the moon, be it soft or hard, by hard landing we mean a crash, is now off the agenda as far as I understand, and it looks as though, yes, the spacecraft will in fact collide with Earth. And if I might just mention, one of our listeners didn't exactly take us to task, but did mention something that I didn't have time to talk about last week when we were discussing this, and that is that the launch vehicle that took Peregrine into orbit also carried another experiment, another spacecraft, or another experiment on board, which contained once again human remains, of which there were rather a large number. These are essentially people's ashes, many of whom were connected with Star Trek, and that was quite an absolutely successful launch. That capsule has gone into a heliocentric orbit, which means it will be for all time orbiting our planet, our sun, along in a similar orbit to the Earth. So one of our listeners actually commented that her husband's ashes were on that space flight. So that's a lovely touch to add to our coverage of that.
Yeah, it gives us kind of a direct connection to it in one way, I suppose. And I'm glad they came forward and told us about it, because it's certainly got a lot of chatter on our social media platform. So thanks for letting us know. And it must have been quite an emotional thing to be involved in too. So Peregrine, unfortunately, all is lost there by the sound of it. Let's look at this next story, Fred, about this dark energy survey. And you always hope with a survey that you come up with answers. We've come up with huge questions.
Yeah, that's right. So the dark energy survey is an international collaboration, which I think has been running for best part of a decade. Using large telescopes, which have been used to make measurements of, supernovae, explosions, and things of that sort. In fact, one of my close colleagues is a member of the Dark Energy Survey, and unfortunately, he's on holiday at the moment till the end of the month, so I can't ask him about this. But at the 243rd meeting of the American Astronomical Society in New Orleans this month. That's the American Astronomical Society always has its meetings right at the beginning of the year, which is great because you get lots of good news stories coming out of it. This is one of them. So some of the results were presented of the Dark Energy Survey were presented at that meeting. So what's dark energy? We know from measurements starting back in 1998 that the expansion of the universe is not slowing down, which is what was widely believed before that the expansion is actually accelerating. And that gave rise to a Nobel Prize. I think in 2011, 3 Nobel Prize winners shared the prize for their contribution to that discovery that that the universe is expanding ever more rapidly. And that's attributed to something we call dark energy, which is an energy possessed by space itself. It's a thing that's common to the whole universe, unlike dark matter, which is actually a substance, one albeit that's invisible, but it likes to be where normal matter is, because we think the two tend to go together, whereas dark energy is everywhere. It's a property of the universe as a whole. And now the early days of dark energy studies were sort of perhaps taken or commenced with a very broad-minded attitude as to what this thing might be. And there were a few suggestions. One of them I remember was quintessence, a fifth fundamental force of nature, with a lovely name, quintessence. It goes back actually, I think, to ancient Greek philosophy. Quintessence would have been something that would actually basically evolve with time. Whereas as time went on, it looked as though an alternative explanation was more likely to be correct. And that is that dark energy behaved in a way that was consistent with something that Einstein introduced back in the 30s. Back in the 20s, something called the cosmological constant, which was a fudge he made to his equations of relativity to make the universe not expand. Because at the time he did this, he didn't know the universe was expanding. And in fact, he called it his greatest blunder, the fact that he put this cosmological constant into the equations not long before it was discovered that actually it wasn't needed because the universe was expanding. But the fact that the universe is expanding ever more rapidly suggests that there is actually a cosmological constant. And that was the other theory that has, I guess, become more widely held as being the reality. So what's the cosmological constant? Why is it different from quintessence? The bottom line is that it doesn't evolve over time. It is something that is a property of space itself that is constant. Hence the name. But that means that as space gets bigger, the amount of energy that the cosmological constant puts in increases. So space gets bigger and the energy increases as well in a sort of linear fashion because it's a constant. Now, to cut a long story short, the results of the Dark Energy Survey actually suggest that is not quite the case. There is basically a property which we call the equation of state, and there's a number you can attach to that. If dark energy is the cosmological constant, then the equation of state is exactly -1. But it's starting to look as though that is not the case, and the answer looks like it might be something like -0.8 rather than -1. -0.8 is the best figure they've got for it. And that then suggests that it's not the cosmological constant, that there's something that actually does evolve with time as the universe ages. I don't know whether that's a clear explanation or not, Andrew, but it's the best I could do.
well, it's certainly an explanation, but it's very confusing. So what they're suggesting is up until now we thought this, we've done this survey, now we don't think this anymore, maybe. Is that the best way to describe it?
Yeah, with a level of uncertainty that actually kind of I suppose it tends to eliminate the idea that it's -1. I think they've got plus or minus 0.18 on the error bars. And that means that there is still a chance of it being -1 at the level of 1 in 20. So it's a 5% chance. But the bottom line, and it comes from a comment by one of the scientists involved with this survey, the bottom line is as usual, scientists want more data.
Yeah.
And so it looks as though there is more research needed, some of which will undoubtedly be done by the new Vera C. Rubin Observatory in Chile, an 8.4 meter telescope that will survey the universe, I think, every 3 days, or the whole sky, to give us a picture of what we call transient events and supernova explosions, which is what you base these measurements on, are transient events. So there's more to come. There is more to come.
I'm glad to hear that, because if we stop there, we'd just be, forever scratching our heads and confused. I've heard the term quintessence before.
Okay.
I watched the movie the Secret Life of Walter Mitty, not the original one, but the remake from a few years ago now. Great film, but they do actually use the word quintessence in the dialogue of that film to describe a photograph.
Well, there you go. There you go.
It's a great word.
It's a nice word. That's right. So maybe it'll come back into vogue for dark energy if we can rule out the cosmological constant. Maybe quintessence is what it is.
I read the other day there's a university in the United States that every year runs a list of words they want to revive from Old English, and the one I liked that they want to bring back this year is, it describes heavy rain from a thunderstorm. It's called thunderplump. I reckon they should bring that back. That's a great word.
We get that, and we're supposed to get that this afternoon, actually, here in Sydney. So I'll tell people that we're experiencing a thunderplump. I love that.
That's the word, yeah, it is. All right, we'll leave that there, but I'm sure in future episodes of Space Nuts, we will be again looking at dark energy and the cosmological constant. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
This next story is, I suppose, slightly related to the one we just did, Fred, and this all centers around a megastructure. Now, we're not talking about a giant space station here. We're talking about a giant series of, I don't know what you'd call them. They're calling it a cosmic megastructure. Do you want to explain first up what that actually is?
It's a bunch of galaxies, basically. So the structure of the universe, the 3-dimensional structure of the universe, which is something that has been, a hot topic in astrophysics and cosmology for several decades. And actually, in fact, our telescope, the Anglo-Australian telescope, was one of the pioneering facilities that allowed us to map that with the 2DF spectroscopy system, something that measures the redshifts of galaxies 400 at a time rather than one at a time, which is what it used to be. So the discovery that came from that sort of work, and this was in the early 2000s, is it kind of confirms what was previously thought. There is a kind of honeycomb structure within the universe that galaxies form almost in sheets and filaments along what is called the cosmic web, which is predicted by, what we understand the Big Bang to have been like, that you would get this web of material because we think it actually, the framework itself is dark matter, and the galaxies cluster around this dark matter to form a visible version of a dark matter web, because the galaxies shine and dark matter doesn't. Now, typically, so if you think of the universe as being like a foam, a foam of soap, except the soap is replaced by galaxies, and it's all on a very large scale. Typically, the voids within this foam of galaxies would be of order 100 million light years, thereabouts. That's the typical size of a void in the cosmic web. And so that seems to be an inbuilt principle of the universe, and it reflects something that we call the cosmological principle, which is that the universe is effectively the same in all directions. That the universe is homogeneous. It's not clearly because it's got this structure in it, but by and large, you look in any direction and you see the same kind of structure. That's the basic cosmological principle. And actually, to be more precise in what I've just said, it states that above a certain spatial scale, and that's typically 100 million light years, above a certain spatial scale, the universe is homogeneous and looks identical in every direction. And that's basically what we've thought to date. However, along comes, another paper at the 243rd meeting of the American Astronomical Society. I told you there a lot of interesting research comes out of those meetings, Andrew, that says there is something that is quite clearly a structure, and it's a megastructure, an arrangement of galaxies, but it's much, much bigger. In fact, it's a ring with a diameter of not 100 million light years, but 1.3 billion light years. So you're talking about something, more than 10 times the scale of what you think is the biggest thing in the universe. It's being, guess what it's being called, Andrew? And it's big.
Not the big ring.
Yes, it's the big ring.
Here we go again. Astronomers naming things.
Curiously, I should say it's actually in the constellation of Boötes, which is a northern hemisphere constellation. But, and again, this is something that's emerged from these large-scale studies of the structure of the universe. Right next to it, and about the same distance away, is an arc, a separate structure, which is an arc of galaxies. And that's been called the Giant Arc, of course, which, well, to the map I'm looking at, which is actually courtesy of The Guardian, it's their article on this, looks almost as though these two structures are concentric. The big ring, 1.3 billion light years in diameter, and sort of sharing a similar center, a giant arc of galaxies, which is even further away. So you're looking at structures that are much more coherent, if I can put it that way, than what we've expected to see. In fact, the giant arc is about 3.3 billion light years long. And so they're both bigger than we expect. And it suggests, as The Guardian says, that this raises the possibility that these two structures are part of a connected cosmological system. And it's bigger than anything that we have expected to see so far. And I should just explain, sorry, Andrew, just to explain where the data come from. It's from a similar survey to what our 2DF survey was on the Anglo-Australian telescope, but it's bigger. It's called the Sloan Digital Sky Survey. And it's a catalogue, actually, in this case, of distant quasars. But quasars are just delinquent galaxies, but they're brighter than normal galaxies, so that you see them from billions of light years away.
As I was going to suggest, they think this ring that we've just been talking about is actually more like a corkscrew, except we're just looking at it end on, so it looks like a ring from Earth, but it's more of a corkscrew of galaxies, isn't it?
Yeah, that's right. Exactly that. That you've got because we're looking end on. It's like looking at a spring, a spiral spring end on. It looks like a circle, but if you look at it sideways, it's got a helical structure, and so it's not really. It's not like a spring. It's probably like a very shallow spring, but a spring that's aligned face on with the Earth, with our own planet or with our own galaxy. Let me, if I may, quote from the Guardian article on this, which was actually written by Hannah Devlin, who's one of their science correspondents, because this really puts the conundrum very, very nicely. Cosmologists are unsure what mechanism could have given rise to the structure. One possibility is a type of acoustic wave in the early universe known as baryonic acoustic oscillations that could give rise to spherical shells in the arrangement of galaxies today. Another explanation is the evidence of the existence of cosmic strings, hypothetical defects in the fabric of the universe that could cause matter to clump along large-scale fault lines. Now, that's a really interesting suggestion, because cosmic strings have been discussed, in the theoretical world of astrophysics many times before, but there's never been any evidence that they exist. They are essentially, as it says, they're zero-dimensional. They've only got one dimension. Sorry, put it that way, and that's the length, which is why it's a string rather than a ball or something. So it's got one dimension, and it is a defect in space-time. And just going back to the other possibility that was mentioned in that little passage, a type of acoustic wave in the early universe, we do see evidence of those, because the spottiness of the cosmic microwave background radiation, that's the slightly hotter and colder regions, even though it's only 0.0001 of a degree, the difference, that is assumed to be caused by these acoustic waves. In other words, the bang of the Big Bang, acoustic waves in the fireball that we can still look back and see over the distance of about 13.8 billion years look back time, if I can put it that way.
Bottom line is, though, theories aside, and you can only have theory, but we really don't know why these things exist, do we? Don't know what the mechanism was or how it happened or anything like that.
Yes, that's right. It underlines something that's the importance of something that's always been very close to my heart in the world of astronomy, because that's what I used to do when I was a practicing astronomer rather than a bureaucrat. It underlines the importance of large-scale surveys, the idea of mapping the sky in very large scales. You see, if you're only doing what we would have called pencil beam surveys, where you look at a small area of sky and probe the distance of galaxies along that line, it doesn't tell you anything about these large structures. It's only when you actually look at huge swaths of sky that you can detect things like the Big Ring. And as time goes on, maybe these surveys will progress more widely, and you'll get the even bigger ring. Who knows what we might find as these data are analysed. And just one more footnote to this, if I may. It was one reason why back at the turn of the millennium, the United Kingdom Schmidt telescope, which is a telescope very close to my heart. I used to be its astronomer in charge at the the Australian Astronomical Observatory. We did a survey which was the whole of the southern sky of this kind, and that was its strength. The fact that with a wide-angle view in a telescope, the Schmidt telescope had a 6-degree field of view, you could do these surveys and probe large swathes of the universe. Where it fell down was that a 1.2-meter diameter telescope can't look all that far into the universe. We could only look out about 500 million light years. Whereas we're talking now about several billion light years, because it was done on a bigger telescope with greater sensitivity.
Well, all I can say is if there's a big ring that contains billions and billions of stars, you're going to have a big pharmacy with a lot of big bottles of hemorrhoid cream nearby, I reckon, because that's too hot to handle. I would also go as far as doubling down on that terrible joke by saying, hang on a minute, you're going to love this one. You did say that this was found near the constellation of Bootes, something I've been trying to avoid. Oh,
dear. Righto. I'm going to touch that.
We'll leave it there. But if you want to read that story, it's on the Guardian.com website. A good read. It's been a well-written article. Even though it tells us this thing exists, we really do not at this stage know why. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
3, 2, 1.
Space Nuts.
Okay, Fred, time to get to our Q&A section, and this is where we hand over to the audience who ask us questions that sometimes we wish we could avoid. But anyway, now I've got one here. It's not so much a question. This comes from something we were talking about last week. This is Emery.
Hello, Andrew and Professor Watson. This is Emery Stagmer, a.k.a. Fax Headroom, calling in from Baltimore, Maryland in the United States, the Eastern Seaboard. I just listened to episode 386, and I got, unfortunately, a correction for Professor Watson. The pressure on Titan is actually only 1.5 bar. That's actually pretty tolerable for humans. We could actually walk around on the surface with just something to keep us warm because the ambient temperature there is about 95 Kelvin. Been a listener for about 2 years. Great podcast. Listen every week. Thanks a lot. Keep it up. Thanks.
Thanks, Emery. Okay, yeah, all right. You were thinking of Venus, I think, when we discussed that.
Yeah, I did. It's a long time since I've looked at the figures, so I just pulled the first number out of my head. I knew it was more than atmospheric pressure on Earth. So, thank you very much, Emery. And point taken. You're absolutely right. I should have looked it up. Sometimes when we get these questions and comments in, I'm very much working on the long end of the distant end of a memory, because yes, of course, I've written about things like that. And Titan, such an astonishing world that you really are. I find myself captivated by just thinking of what it would be like there. But a good point that we could walk around with perhaps not quite normal clothing, but something to keep us warm. But it doesn't have to be a pressure suit because the pressure's more than we're used to on the outside.
Perfect. Well, yeah, just don't like I don't like getting cold.
While we're doing the mea culpas, Andrew, I might just mention, in case he's listening in, that we took note of some comments from Jens in Sweden. Which came in just before Christmas, and we'll talk about those as well. Jens is also quite correct in pointing out some flaws in things that I said on the spur of the moment, because yes, I'm cast onto my own devices when I'm answering these questions. They have no warning. I don't know what's coming up, and usually it's relying on my memory, which is, as time goes on, getting more and more faulty. However, we'll keep going until people just switch off and don't listen anymore.
Well, that's why we created Space Nuts in the first place, to keep you sharp. That was the only motivation for it.
Well, it's doing a good job. Thank you.
Okay, let's move on to a question from Scott.
Hey, this is Scott from Oregon. Just wanted to ask if we know how old the water is that is on Earth. Was it existing before the sun or what? Thanks, guys. Really enjoy the show.
Okay. How old is the water on Earth? Now, there's varying theories as to where it came from. Some theories are, based on it being dumped here by asteroids. Other theories are that it was already here when the Earth started to form and it just leached out. It's probable that both hold water. Does that mean that the water on Earth could vary in age, or do we take it back even further and say, well, it all sort of happened at once, so the water is the same age regardless?
That's a great answer, Andrew. Oh, good. You probably said what I was going to say. You're right that two main theories. One is that water has arrived on Earth from comets and asteroids impacting in the early history of the solar system, and the other that the water was there all the time because the cloud of gas and dust that the Earth, that the solar system condensed out of, contained water, and some of that water found its way into the rocks and eventually leached out, as you've said. Either way, I think the answer is right, that it predates the Earth. So probably the simplest scenario to visualize is the impact scenario. So you start off with a cloud of gas and dust, which collapses under its own gravity. The middle part of that becomes very hot and forms the sun. Meanwhile, a rotating disk of material, dust, gas, and other rubbish, swirls around the infant sun, and the planets basically, by a process of accretion, which is stuff sticking together, they grow in that disk. But that model tends to leave behind a sort of shell of the original gas and dust in the cloud from which the sun formed, at a much greater distance than any of the planets, way in the depths of of space, beyond the most remote planets and trans-Neptunian objects and all the rest of it. So we've got this shell of ice because it's cold enough there that it becomes ice. It's not vapor anymore. It's actually lumps of ice. And those lumps of ice we call comets. They've got dust embedded in them. And the thinking is that in the early history of the solar system, when there was debris everywhere, that some of those things impacted the baby Earth and brought the water. So what you're learning from that is that the H2O molecules were probably in existence long before the solar system came into being, that they were present in the cloud of gas and dust which was within our own galaxy, and that is the origin of the water. Water being the most common two-element molecule in the universe. That's the key thing to this. It's everywhere, not just here. It's everywhere.
Yeah, and there was a time we didn't realise that. We just thought, well, we've got water here, but we can't see it anywhere else, so it can't exist.
Yes, but it does. And we actually know there's more water in the solar system than we've got on Earth, more liquid water. I think Europa, one of Jupiter's moons, which has a layer of ice with a sub-ice ocean underneath it and a rocky core, we think there's at least twice as much water on Europa as there is in all the Earth's oceans. And when you get to Titan, which has a similar structure, it's even more. It's probably 3 or 4 times more than all the Earth's oceans. So even in these little bodies that we find in the solar system, there's more water than we have on our oceans. And then the comets themselves are very rich in water because that's what they're made of.
Yeah. Okay, thank you, Scott. Lovely to hear from you. Hope all is well in the great state of Oregon. Now, I got a question from Paul. It's a text question, but I've managed to lose it. It was a very short question. I think I can paraphrase, but I'm not even sure if we did this one before. That's how well my brain's going at the moment. But he was asking about slingshotting around planets and why we accelerate if we're going in at certain velocities. And I think he quoted some sort of formula. Why would we accelerate around a planet or another body? How does that slingshot effect work? Someone else might have asked that question.
Yeah, maybe so. I think we did it towards the end of last year. But the bottom line is, yes, so that you intuitively you think, okay, your spacecraft is being pulled in towards a planet by the planet's gravity, and then it's leaving the planet. And so it should, lose as much energy when it leaves as it gains when it arrives. And from the viewpoint of the planet itself, that is absolutely correct. As far as the planet's concerned, the spacecraft accelerates towards it and then accelerates away or decelerates away, and the two balance out, so there's no change. But the trick is that the planet is moving in its own orbit around the sun. Right. And so when you look at it in a coordinate system that's centered on the sun, what happens is that some of the momentum of the planet is actually transferred to the spacecraft, and the spacecraft gets a boost, a slingshot boost, which is really well worth having, as we know from the many space flights that have used it. So it's all about the motion of the planet, not just its gravitational attraction.
Does that mean that if you were to get a slingshot off a fast rotating planet, you'd get a really good slingshot, or doesn't it work that way?
Fast revolving around the sun, yes, you would. Yeah.
Okay. So it's the revolution around its parent star that makes the difference, not the rotation of the planet itself.
Yeah, there is actually an effect with the rotation, but it's a much more subtle one. And I think we've talked about this before. I think one of the interesting discoveries is that if you come in from approach the planet obliquely, in other words, say below its equator, then that affects the amount of slingshot that you get. So it's the rotation of the planet that's now coming into play. Maybe that's for very close slingshots.
And of course, the rotation of the planet is you get a good effect of when you're launching a spacecraft from the surface of the planet.
Yes, that's right. Yeah,
from the equatorial areas, because you get a better assist. Is that right?
Yes, exactly. Because you're pushing you can use the rotation of the planet, in this case, the Earth. It's about 1,600 kilometers per hour that you get free if you launch on the equator. At our latitudes, it's more like 1,400 kilometers an hour, but it's enough to make a difference, and it's enough to make space launches from these equatorial regions very important.
Okay, there you go, Paul. Sorry, I lost your question, but I know we got one like it last year, and it's good to go over it again. It's really interesting science. Next up, we go to Brisbane.
G'day, Watto and Dunks. Ash in Brisbane here. Guys, I just wanted to touch on a theoretical question. Floating cities in the atmosphere of Venus, but not ones that have humans on board. Maybe having some algae up there to transform some of the carbon dioxide due to photosynthesis, and maybe some OH generators that we've been working on here on Earth. Would that clean up some of the atmosphere? And if so, could you potentially, over a long period of time, cool the atmosphere? Interested to hear your thoughts. Thanks, guys.
Wow. We're going down the Martin track of terraforming again by the sound of it. It sounds like it would
be natural terraforming, but
yeah, it could be too big a project, couldn't it? Or if you did it over a long period of time, maybe eventually you could make some kind of difference. But Venus it's like trying to cool down an oven with a drop of water.
Yeah, that's right. So yes, if you've got 1 million years, that might be good. It might work. But so Ash raises a really interesting point, though, because the upper atmosphere of Venus is a bit of a hot topic in terms of our understanding of the potential for living organisms. That because there are levels in Venus's atmosphere which are actually quite equitable, quite climatically what you might call normal, with pressures and temperatures similar to what we have here on Earth. And so that there is a suggested picture that perhaps within those regions of Venus's atmosphere, we could find microorganisms which are indigenous. They've originated there. And that you'll remember a couple of years ago, there was great excitement when scientists at the James Clerk Maxwell Telescope in Hawaii thought they had detected phosphine in Venus's upper atmosphere, which would suggest biological origin. Phosphine's not easily produced by rocky planets without life processes. So that's, it is an area of great interest. Now, whether you could actually generate enough OH to essentially modify Venus's atmosphere, as you are, Andrew, I'm a bit doubtful about that. It's a big project. Venus at the surface has an atmosphere, and I think I'm pulling this number out of my memory accurately, of the order of 100 times the pressure of Earth's atmosphere. So there's a lot of atmosphere that you've got to change. And I, in fact, think that the idea of terraforming Venus really is a non-starter under any circumstances, because we don't know too much about the geological state of the surface. We know lots of, we think there are active volcanoes on Venus. There's evidence to suggest that there might well be, which is, putting it into a different perspective.
Yeah,
great suggestion though, Ash. I like your thinking.
He's always got some interesting ideas, has Ash. I'm not so sure about the Watto and Dunks show though. That might.
I didn't see that.
That's how he started off. Hello, Watto and Dunks.
Should be the other way around, shouldn't it?
Doesn't matter.
Dunks and Watto.
Oh no, I think it's got more of a ring to it the other way. And you're the star. I'm just the idiot.
All right, okay.
Pushes the buttons, and I'm not doing it very well today. But thanks, Ash. Great.
I don't think you should.
Great to hear from you. Now, we've got one more quick question. I know we only usually do 2 or 3, but this one came in via our Spotify platform, and it's a one-liner. Hello, if stars are made of the same stuff as humans, are we stars? I am 6. That's from Nomi. Hi, Naomi. Great to hear from you. It's great to hear some young listeners getting involved. So if stars are made of the same stuff as humans, are we stars? Now, Naomi, that reminds me of a documentary the BBC did some years ago called The Stars. And there was one episode dedicated to the sun. And the big revelation was when humans discovered that the sun was actually a star like all the other ones twinkling in the heavens. And the show concluded with the claim that we were all made of stardust. So my answer to you is yes. What do you say, Fred?
Yes, being made of the same stuff as something doesn't make it the same.
No, we're not stars.
Any comment?
Although we do label
That's right.
people that.
Well, actually, yeah, Nomi's a star, definitely. There's no question about that. Great question, but yes. So, but it's the correct thinking because of the material that makes up you and me and everybody else in the world. I mean, the most important things are carbon, hydrogen, oxygen, nitrogen, a few other things. Small traces of other elements. But that's what we're made of. And all of those except hydrogen come from the inside of stars because these chemical elements are all produced in the cores of stars. So they were generated in the cores of stars. The stars fell apart one way or another at the end of their lives, and that put the raw material for humans into space where other stars formed and basically formed planets, and suddenly here we are. The hydrogen, most of it came from the Big Bang itself. So your hydrogen is even older than your oxygen, nitrogen, and carbon. Hydrogen is the oldest of the elements because it was formed. Its nuclei were formed in the aftermath of the Big Bang. So since most of what humans are made of is water. I can't remember. Is it 75%?
Yeah, something like that.
That means, and so in a water molecule, 2 out of the 3 atoms in a water molecule are hydrogen. So 2/3 of your 75%, which is 50% of the atoms in your body, come from the Big Bang. Which is why you feel old these days. Yeah.
Yeah.
The 13.8 billion year old hydrogen.
Wow. Well, that explains the aches and pains. Thank you, Naomi. Great to get your question. And please, if you've got any more questions, send them in to us. We'd love to hear from more of our young audience, of which there are, well, we now know 2. Always good to get feedback from everybody. If you do want to send us feedback or some questions or send us a what if or anything along those lines, you can do that through our website, spacenutspodcast.com or spacenuts.io. Click on the links to send us your text or audio questions. Fred, that brings us to the end of another show. Thank you, sir.
Well, it's a pleasure. It's been a very stimulating show. I only made 6 mistakes in this one, but that's all right.
Yeah, we'll get feedback on that. I'm sure we'll be.
Yeah.
As I always say, we only strive to be adequate.
Great. And it's great that we've got listeners who, are happy to pick up on the howlers because I'm always willing to be corrected.
As I am, which I'm very much used to. Thanks, Fred, as always. Catch you on the next episode.
Sounds great. Take care.
Fred Watson, astronomer at large, and Hugh in the studio. I wish all the very best in editing this particular episode, given all the technical dramas we had. And from me, Andrew Dunkley, thanks for your company. Catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.
And if you've been listening to the live version, thanks for your patience.